Welcome back to NexMEP, your one-stop guide to MEP engineering excellence. I'm so glad you're here. In today's video, we're diving deep into the fundamentals of electrical concepts, the building blocks that every MEP engineer, electrician, or engineering student absolutely must know. Whether you're just starting out or looking to refresh your basics, this video is for you. We'll be covering 4 key topics today: power, single vs 3-phase supply, power factor, and types of electrical loads. So let's get right into it. Before we jump in, here's a quick look at what we'll be covering in this video. First, we'll understand power and the golden formula P equals V times I. Then we'll compare single-phase and 3-phase supply. After that, then comes one of the most important concepts in real-world engineering, power factor. And finally, we'll wrap up with the types of electrical loads. Stay till the end because there's a quick summary to help everything stick. Let's begin. Alright, let's start with the most fundamental question: what is electrical power? Simply put, power is the rate at which electrical energy is used or consumed. Think of it this way: voltage is the push, current is the flow, and power is the actual work being done. And the formula that ties it all together is P equals V times I, power equals voltage multiplied by current. Now let's make this real. Your LED bulb uses just 10 watts, that's very low power. A ceiling fan uses 70 to 80 watts, medium power. But a heater? It uses 1000 to 2000 watts, that's high power. And that's exactly why when you switch on a heater, your electricity bill shoots up. The more power a device consumes, the more it costs you. Now, power is measured in watts. For small devices, we use watts, W. For larger systems, we use kilowatts, that's 1000 watts. And for power plants or huge industrial setups, we use megawatts. Now here's something very important for MEP engineers: in AC systems, power is actually split into 3 types. First, active power, measured in kilowatts or kilowatt. This is the actual usable power that does real work, like running a motor or lighting a lamp. Second, reactive power, measured in kVAR. This is energy that goes back and forth but doesn't do any useful work. Third, apparent power, measured in kVA. This is the total power supplied by the source. Understanding these 3 is critical when you're designing electrical systems for buildings and industries. Great, now let's move on to our second topic: single-phase and 3-phase supply. Let's start with single-phase. A single-phase supply uses just 1 live wire and 1 neutral wire. In India, the standard single-phase voltage is 230 volts. The important thing to note is that the power flow in single-phase is pulsating, meaning it's not constant, it goes up and down like a wave. Single-phase is commonly used in homes, small shops, and small offices. Think about the devices at home: your lights, your ceiling fans, your TV, your fridge, all of these run on single-phase supply. It's perfect for low-power applications. Now let's look at 3-phase supply. 3-phase supply uses 3 live wires plus 1 neutral wire. In India, the standard 3-phase voltage is 415 volts. Unlike single-phase, the power flow in 3-phase is continuous and smooth, because the 3 phases take turns delivering power, keeping the supply steady at all times. 3-phase is used in industries and large commercial buildings. Think of heavy equipment, motors, lifts, compressors, and large machinery. All of these need 3-phase supply. 3-phase is the go-to choice for high-power applications. So how do single-phase and 3-phase compare? Here's a quick side-by-side. Single-phase has 1 phase, 3-phase has 3. Voltage is 230 V versus 415 V. Power flow is pulsating in single phase but continuous in three-phase. Single phase is used in homes while three-phase is used in industries. And in terms of efficiency, three-phase wins. Here's a brilliant way to remember this: imagine pushing a heavy cart. With single phase, it's like one person pushing alone, the effort is uneven and tiring. With three-phase, it's like three people pushing together, smooth, powerful, and efficient. That's why three-phase is always preferred for heavy industrial loads. Motors run smoothly, there's less vibration, and the whole system is more efficient. Now we arrive at one of the most important concepts in electrical engineering: power factor. Power factor tells you how effectively electrical power is being used. It's a number that ranges from 0 to 1. The closer it is to 1, the more efficient your system is. Remember those three types of power we discussed? Real power in kilowatt is the power that actually does useful work. Reactive power in kVAR goes back and forth without doing anything useful. And apparent power in kVA is the total power supplied. Power factor is simply the ratio of real power to apparent power. Here's a simple example: a factory with many motors. If the power factor is 0.7, the system is drawing more current than it needs, causing losses and even penalties from the electricity board. But if you improve it to 0.95, you draw less current, save money, and run a more efficient system. So why does power factor matter so much? For reasons. Number 1, electricity bills. Industries with a low power factor get penalized by electricity boards and face higher demand charges. A high power factor means savings. Number 2, losses and heating. Low power factor means higher current flows for the same load. Higher current means more I²R losses, which means cables heat up and equipment wears out faster. Number 3, equipment sizing. With a low power factor, you need bigger cables, bigger transformers, bigger generators. But with a high power factor, you can design a smaller, more efficient system, saving both money and space. Number 4, system performance. Low power factor causes voltage drops and poor motor performance. High power factor gives you stable voltage and smooth operation. So how do we improve it? The most common method is installing capacitor banks. You can also use automatic power factor correction panels, called APFC panels. Capacitors supply reactive power locally, which means the source doesn't have to, and the power factor improves. Now let's talk about types of electrical loads. An electrical load is simply any device or equipment that consumes power. There are three main types: resistive, inductive, and capacitive. Let's start with resistive load. A resistive load opposes current without storing any energy. The current and voltage are perfectly in phase with each other. These loads simply convert electrical energy into heat or light. Classic examples are heaters, iron boxes, and incandescent bulbs. Think of it like a straight road: no delay, no storage, just direct conversion of power. Next, inductive load. Inductive loads store energy in a magnetic field through coils of wire. In these loads, current lags behind voltage, meaning current comes a little after the voltage. This lag is what causes a low power factor. Common examples are motors, fans, and transformers. Think of it like a heavy vehicle: when you press the accelerator, it takes a moment to respond. The third type is capacitive load. Capacitive loads store energy in an electric field. In these loads, current leads voltage, meaning current arrives before the voltage. Capacitive loads actually improve power factor because they supply reactive power. The best examples are capacitor banks and power factor correction panels used in industrial buildings. Think of it like a spring: it reacts instantly and pushes forward. In a real building, you'll find all three types. Lights are resistive, fans and pumps are inductive, and capacitor panels are capacitive. When you combine all three types in a building, the overall system behavior depends on which type dominates. That's why MEP engineers always do a load calculation before designing a system. Alright, let's quickly recap everything we've covered today. 1. Power. It's the rate of energy consumption. The formula is P equals V times I, measured in watts. More power means more consumption and a higher bill. 2. Single vs 3-phase. Single phase is for low power loads like homes, running at 230 volts. 3-phase is for heavy industrial loads, running at 415 volts with smooth, continuous power. 3. Power factor. PF measures how efficiently you're using electrical power. Closer to 1 is better. Low PF causes losses, overheating, and penalties. Improve it using capacitor banks and APFC panels. 4. Types of loads. Resistive loads convert power to heat or light. Inductive loads run motors and cause low PF, capacitive loads correct power factor. And that's a wrap for today. I hope this video gave you a solid foundation in fundamental electrical concepts. If you found this helpful, please like this video, share it with your friends in the MEP or electrical field, and subscribe to NexMEP for more weekly content. Drop your questions in the comments, I read every single one. See you in the next video.